An entity type is like a blueprint for a real-world thing, for example, a student or a car. To store that blueprint in a relational database, we create a relation schema, a table. The formal notation is R open parenthesis A1 A2, a K close parenthesis, where R is the table name and each AI is an attribute, a column. Every attribute of the entity becomes a column, and the entity's unique identifier, its primary key, becomes the table's primary key. For example, the entity type student open parenthesis student underscore id, name, birth underscore date close parenthesis becomes the table student open parenthesis student underscore id primary key, name, birth underscore date close parenthesis. All rows in the table represent individual students, just like each object of the entity type represents a real student. A weak entity is a thing that cannot be identified on its own, and it needs another owner entity to give it an identity. Think of a dependent, spouse, or child that only makes sense when we know the employee they belong to. In the ER diagram, the weak entity has a partial key, for example, dependent name, and a double-bordered rectangle. When we turn it into a table, we combine the primary key of the owner with the partial key to form a composite primary key. Example, dependent emp id foreign key, dependent name, relationship, primary key emp id dependent name. Here emp id is a foreign key that points to employee emp id, and together with dependent name, it uniquely identifies each row. Binary relationships involve just two entity types. How we store them depends on the cardinality. One-to-one, each side has at most one partner. We can place a foreign key in either table. Example, each person has one passport. Add passport number foreign key to person or person identifier foreign key to passport. One-to-many, the many side gets the foreign key. Example, a department has many employees. The employee table gets department identifier foreign key referencing department identifier. Many-to-many, we need a new junction association table containing two foreign keys, each referencing one of the participating tables, and the pair of keys forms the primary key. Example, students enroll in courses. Create table enrollment with student identifier foreign key, course identifier foreign key, primary key student identifier, course identifier. Mathematically, the junction table represents the natural join of the two relations. Enrollment equals student natural join course on the foreign key columns. When a relationship involves three or more entities, we call it higher degree ternary NRE. The safest way to store it is a separate table that holds a foreign key for every participating entity plus any attributes of the relationship itself. Example, a project is worked on by a student under an advisor. We create table project assignment student id foreign key project, id foreign key, advisor id foreign key role primary key student id project id advisor id. If we tried to break the ternary into several binary tables, we might lose the rule that the same student project pair must always have the same advisor, so keeping a single ternary table preserves the original constraint. A composite attribute is an attribute that can be split into smaller parts, like a full name into first underscore name and last underscore name. In a relational table, we store each part as its own column. There is no composite column type. A multi-valued attribute can hold many values for one entity, such as a person's phone numbers. To represent it, we create a new table that contains the primary key of the original entity plus the repeated value, and we make the combination the primary key. Example, person open parenthesis person underscore id pk, name close parenthesis. Phone open parenthesis person underscore id fk, phone underscore number, primary key open parenthesis person underscore id comma phone underscore number close parenthesis close parenthesis. Thus each row in phone lists one phone number for a person, and a person can appear in many rows. Primary key pk is a set of one or more columns that uniquely identifies each row in a table. Formally, primary key is a subset of the relation, and for any two distinct rows R1 and R2 in the relation, the primary key values of R1 are not equal to the primary key values of R2. Foreign key fk is a column or set in one table that must match values of a primary key in another table, ensuring referential integrity. Every foreign key value either is null if allowed or appears as a primary key value in the reference table. Example, order with order ID as primary key and customer ID as foreign key, where customer ID must exist in customer with customer ID as primary key. Participation constraints tell us whether an entity's involvement is total, meaning every instance must participate, or partial, meaning some may not. In the example, the total participation of order in customer means every order must have a customer. We enforce this by declaring customer ID not null and adding the foreign key constraint. After we have turned an ER diagram into tables, we must check that the tables are normalized. That is, they do not contain unnecessary redundancy. This is done by examining functional dependencies, which are statements of the form X determines Y, meaning if two rows agree on the attributes X, they must also agree on Y. Example. In a student table, student id determines name and birth date. First normal form, all columns are atomic, no repeating groups. Second normal form, every non-key attribute is fully dependent on the whole primary key, no partial dependencies. Third normal form, no transitive dependencies. If A determines B and B determines C, then A should not directly determine C unless B is a key. Boyce-Codd normal form, for every functional dependency X determines Y, X must be a superkey. We test each table against these rules, and if a violation is found, we decompose the table into smaller ones that satisfy the higher normal form while preserving data. Mathematically, a decomposition R determines the set R1, R2, and so on is lossless if the natural join of R1, R2, and so on equals R, and dependency preserving if the union of the functional dependencies of the rise determines the original functional dependencies. A derived attribute is not stored directly. Its value can be computed from other stored attributes. For example, age can be calculated as current date minus birth date. In the relational model, we usually do not create a column for a derived attribute. Instead, we define a view, a virtual table defined by a select query. Create view studentinfo as select student id, name, birth date, date part year age of current date, and birth date as age from student. The view behaves like a table, so programs can query studentinfo.age as if it were a real column, while the database computes the value on the fly. Views can also be used to hide columns, combine several tables, for example showing an employee's name together with department name, or enforce additional security constraints.